Okay, so today we are going to derive a temperature expression for a sphere, graph it, and then find the thermal resistance of the spherical shell. So we're going to start by picking a fun color. We'll do blue. So we're going to start off how we start every problem with a energy balance. So we're going to do in minus out. Actually, I'll do it over here. In minus out wash generation equals accumulation. And since we're at steady state, accumulation is going to be 0. And we're not generating any energy, so that's going to be 0. And that says it here. And steady state. So eventually we get in minus out equals 0, and our in is going to be, we're in QRA evaluated at R minus QRA evaluated at R plus delta R is going to be 0. So we're going to divide by delta R, and that gives us the definition of a limit, and that's going to give us a diffie Q of ddr of, or negative ddr of QRA equal to 0. So we want our expression in terms of R. So we're going to sub in using this expression for Q, and our A is going to be equal to the surface area of a sphere, which is equal to 4 pi r squared. So subbing in those two, we're going to get negative d dr of 4 pi r squared times negative k dt dr equal to 0. So we're going to pull out our constants and get 4 pi k d dr of r squared dt dr equal to 0. From here, we're going to divide over by our constants, which leaves us with the dr of r squared dt dr equal to 0. With this, we're going to move down a little bit. Come back over here. We're going to integrate both sides. And that is going to give us an expression of r squared dt dr is going to be equal to c1, where c1 is the integration constant. So we're going to separate our variables and integrate again, since we still have a differential term. And once we separate our variables, we're going to get dt is equal to c1 over r squared dr. And integrating, we get an expression for t is going to be equal to negative c1 over r plus c2. And since we have these integration constants, we are going to need to invoke some boundary conditions. And for this problem, the boundary conditions are 1 at r is equal to r1, t is equal to t1, and secondly at r is equal to r2, t is equal to t2. And we're going to set up like a system of equations basically with these. So equation 1 is going to be t1 is equal to negative c1 over r1 plus c2. And we're just plugging in like t1 for t and r1 for r. Equation 2, we're going to get t2 is equal to negative c1 over r2 plus c2. So we have two unknowns and two equations. So we are going to subtract 1 from 2. Oh, actually, just kidding. Subtract 2 from 1. And we're going to get t1 minus t2 is equal to c1 times 1 over r2 minus 1 over r1. And then once you rearrange that a little bit to make it a little nicer, you get c1 is equal to r1 minus r2 over r1 r2. Oops, it's c1 times, not equals to. So from here we get c1 so we want to solve for c1. So solving for c1, we get either t1 minus t2 over r1 minus r2 times r1 r2, or this is also equivalent to t2 minus t1 over r2 minus r1 times r1 r2. Either of those are correct. So now that we have an expression for c1, we want to go back to our equations up here and solve one of them for c2. So I'm just going to pick equation 1. So using equation 1, c2 is equal to t1 plus c1 over r1. And so we need to plug in for our c1 here, and I'm just going to choose using this one over here. I'm going to use this one for c1. And, well, actually, I'll just do either one. I'll just make them equivalent. So I'll do both depending on which one y'all want to pick. So plugging in for C1, we get C2 is going to be equal to T1 plus T1 minus T2 over R1 minus R2 times R2. Just kidding. I don't like the way that one works out. I'm going to choose this one. So we're going to T1 is T2 minus T1 over R2 minus R1 times R1 R2 over R1. So R1's cancel, and you get C2 is equal to T1 plus T2 minus T1 over R2 minus R1 times R2. So now that we have our expression for C2 and C1, we are going to plug both of those back into our original T expression up here. Where is it? We're going to be plugging them into this one to get our temperature profile. So once we do that and manipulating with a little algebra, we get that T is equal to T2 minus T1 over R2 minus R1 times R1 is 1 minus R. Oops, just kidding. This should, we get, oops, I can't do math. So we're going to get T2 minus T1 over R2 minus R1 times R1 R2 over where is it? 2 over r plus c2, which is t1 plus t2 minus t1 over r minus, or r2 over minus r1 times r2. And so that, oops, this should be a negative 2. There we go. So once we have that, we're going to go simplify and get t is equal to t2 minus t1 over r2 minus r1 times r2 1 minus r1 over r, and then add that t1. So we're just pulling this expression out because we have this term minus this term. Okay, so now that we have, this is our temperature profile. Now that we have this is our final temperature profile answer. We can see that temperature varies with inverse R. So T varies with inverse R. So when we graph that, it's going to look something like this. Sorry, I'm not an artist. But we know that T1 is up here, T2 is down here, R1, R2, T1 is greater than T2. Our graph is going to look something like that. So that's how T varies with R. It's an inverse graph. So now that we have that, we are going to work on finding the other part of the problem, which was, oh man, I forgot. Oh, thermal resistance. We're going to find the thermal resistance of the sphere. So with that, we know that QR is equal to negative K dt dr. So we want this. We want dt dr. And so we're gonna take the derivative of our temperature profile we derived before of temp profile. So our dt dr is T2 minus T1 over R2 minus R1 times R1 R2 over R squared. And so now that we have that, we're going to plug that into this. So our QR is going to be equal to negative K times T2 minus T1 over R2 minus R1 times R1 R2 over R squared. And so if we just distribute that negative through, we're going to get K is equal to T1 minus T2 over R2 minus R1 times R1 R2 over R squared. So Q at any R, so we want to find big Q, and big Q is equal to QR times the area. And we already established that our area is 4 pi r squared, and our Q is this expression. So if we find big Q, we're going to get 4 pi r squared times K over T, or times T1 minus T2 over R2 minus R1 times R1 R2 over R squared. Canceling out like terms, we get Q is equal to 4 pi K times T1 minus T2 over R2 minus R1 times R1 R2. So basically we can just rewrite it as solving for delta t, because delta t is going to be equal to QR. So T1 minus T2 is equal to Q times R2 minus R1 over 4 pi K R1 R2. So like we said, this is going to be our delta T. This is Q, so this has to be our R term. So R is equal to R2 minus R1 over 4 pi K R1 R2. And then if you further simplify that or want to simplify that, that comes out to 1 over 4 pi K times 1 over R1 minus 1 over R2. So this is the thermal resistance required for R2 to be greater than R1. And even though like R2 might become, if R2 like goes to infinity, the value of R still only just goes to 1 over 4 pi KR, which is fairly small. But that is a example on how to derive the temperature profile and thermal resistance of a sphere. Thanks for watching.